Welcome back to Mechanical Design 1, Stress, Strain, Deflection. We'll continue with another topic, stress concentration. The next topic is stress concentration. The outline of this section is main concepts of stress concentration, static loading, dynamic loading, geometric factors, and how to avoid stress concentrations. So here we see a bar or a beam, okay, with some notch and filter. And this type of abrupt changes in the cross-sectional area is very common. Because so far we had ideal cases of a specimen for tensile test, and that specimen was a cylinder. Yes, but that was a perfect cylinder. Or we've done a calculation on how we could find torsion stress, torsion basically shear stress on a circular bar. How we could find a transverse shear on a beam. But those beams were perfect beams, yes, either perfect circular or cubic, yes. So they had a perfect shape without these notches and filters or any abrupt changes. But these shapes are necessary to install other mechanical components. We want to install, for example, gears, we want to install bearings, we want to have a key slot, and we see that also the key slot creates stress concentration. And we see that what is the effect of these type of abrupt changes in the cross-sectional area. So we could say that these changes create a stress concentration. Here we have photoelastic stress distribution, okay, or finite element analysis stress distribution. This FEA analysis could be done in softwares, or this photoelastic stress distribution could be done by a photoelastic elements or materials. And we see that how a stress distribution changes when it reaches to these type of basically abrupt changes or shapes. Here, where we are far from these shapes, we have normal stress distribution, and that is a sigma normal. For example, if we apply a bending moment to this beam, we'll have this linear distribution of stress here at this cross section. But when it comes here to these sections, we need to take it into account, and we need to apply some factors. We have a video here that shows photoelastic demonstration of a stress concentration. Let's watch a video together.
What we're showing here is a 4-point bend setup. There is a bar of plastic in the 4-point bend jig with a notch in it. We're going to use that notch to show the effects of stress concentration. The plastic is photoelastic, and when we put it in polarized light, there will be colors representing the amount of stress exhibited by the material. And so here's the cross polarizers slid into place. And so what you can see is under the loading points there's stress, and then you can even see at the notch that the colors are concentrated. The other thing is this is a bending apparatus, and so what you'll notice in the center is that it will remain pretty much clear, and that's because that's the neutral point, because on the top we're going to have compression and the bottom we're going to have tension. So what we're going to do is we're going to increase the stress, the far field applied stress, and what you'll see is that the stress will be concentrated near the crack tip, or where the notch is. So I'm going to do this side to side, a little bit on each side. And so you notice how the colors increase, but then the distance between bands of color around the notch are smaller and more concentrated. So what we're showing is the stress concentrated around the notch. Now I want to focus in, I want to repeat this experiment, but focus in on the notch. Okay, so now we're showing the notch up close, and you can see that there's kind of this grayish color that representing a relatively small amount of stress. I'm going to increase the stress as before, and you'll be able to see the evolution of the stress concentration adjacent to the notch tip, and how the spacing is a little bit more intense right around the notch tip. So that's the idea of stress concentration that we'll be continuing to talk about.
Okay, so that shows, the video clearly shows that stress concentration happens close to notches or filters, and we see how we could take into account effect of stress concentration in coming slides. The amount of stress concentration in any particular geometry is denoted by geometric stress concentration factor Kt for nominal stresses, or by Kts for shear stresses. The maximum stress at the local stress razor is then defined as sigma max is equal to Kt multiplied by sigma nominal, and tau max is equal to Kts multiplied by tau nominal, where sigma nom and tau nom are the nominal stresses calculated for the particular applied loading and net cross section, assuming a stress distribution across the cross section that would obtain for a uniform geometry. Okay, so let's see what is sigma nominal and tau nominal. For example, in the beam of above figure, the basically previous example, the nominal stress distribution is linear, and at the outer fiber, sigma nom is mc divided by I. Okay, so these are the formulas we already developed. These are the analytical, basically, calculation of stresses, either normal or shear stresses. The stress at the notches would then be sigma max equal to Kt multiplied by sigma nominal, which is mc divided by I. The factors Kt and Kts only take the effects of part geometry into account. Okay, so we need to find only Kt and Kts for notches, filters, key runways, and see how much are those Kt and Kts, which will be topic of coming slides. Before going to that part, we need to differentiate ductile materials and brittle materials under stress concentration. For the ductile materials will yield locally at the stress razor, while the lower stress material further from the geometric discontinuity remains below the yield point. So we said that, for example, we have a notch, okay? So at the notch, we have a stress razor, or we have a stress concentration. We have that Kt, yes, that increases the stress, and the stress could go beyond the yield point, okay? Thus, it is common to ignore the effect of geometric stress concentration in ductile materials under static loading. Why? Because stress goes beyond the yield point, and then we will have a local plastic deformation. That plastic deformation will release stress concentration. The stress for the net cross section is calculated as if the stress concentration were not there. Okay, so for the ductile material, for the static load, we could ignore stress concentration. However, the reduction in net cross-sectional area or in area moment of inertia due to the removed material is accounted for, thus producing higher stress than for an unnotched part for the same overall dimension. So what do we mean by this bullet point here? We said that, for example, stress is equal to normal stress. Sigma x is equal to kT multiplied by sigma nominal. Fine. Okay. KT, we said because the material is ductile, we could ignore kT. KT is 1. But then sigma nominal is equal to mc divided by I. So we see that C changes because of the notch and I changes because of the notch. And we need to take into account the geometrical effect of the notch, not because of stress concentration, not because you have KT. No, we don't have KT is equal to 1 because it's ductile, but cross-sectional area changes, area moment of inertia, I changes, and we need to consider those effects. What about for brittle materials? They will not yield locally. Why? Because brittle materials don't have a room to have plastic deformation. Since they do not have a plastic range, thus stress concentrations do have an effect on their behavior even under static loads. Be careful again, this discussion is about the static loads for both brittle and ductile materials. Once the stress at the stress razor exceeds the fracture strength or crack, a crack begins to form. Okay, so if a stress goes beyond the fracture strength, then a crack starts to open and form at the notch. This reduces the material available to resist the load at the crack. So we are talking at the crack. And also increases the stress concentration in the narrow crack. So the crack itself has a sharp shape, and at the point of the crack we have the sharp point. At the tip of that crack will have a huge stress concentration. The part then goes quickly to failure. So it basically works as a positive feedback loop. Once a crack opens, then it basically develops and grows very quick, and suddenly part breaks at the point of stress concentration. So the brittle materials under static load, the stress concentration factor should be applied to increase the apparent maximum stress. The one exception to this is for brittle cast materials. Okay, so the exception is basically brittle cast material because the cast material has graphits, and those graphits could work as lubricants and stops cracks to develop. Okay, so this is another basically topic, but in general we could say brittle materials, we must consider effect of a stress concentration, and we need to find geometric stress concentration factors, KT and KTS. What about for dynamic loads? Ductile materials under dynamic loading behave and fail as if they were brittle. So regardless of ductility or brittleness of the material, the stress concentration factor should be applied when dynamic loads are present. However, there are still material-related parameters to account for. While all materials are affected by stress concentration under dynamic loads, some materials are more sensitive than others. Okay, so for both ductile and brittle materials, it must be uh, uh, it must be considered. The stress concentration factor must be calculated. But the issue is that for dynamic load, KT and KTS are not solely geometric. It doesn't only depend on geometrical shape of the part, it also depends on material property. A parameter called knot sensitivity, or Q, is defined for various materials and used to modify the geometric factors KT and KTS for a given material under dynamic loading. Determining geometric stress concentration factors. Figure shows an elliptical hole in a semi-infinite plate subjected to axial tension. So here we have our elliptical hole here in this plate. The hole is assumed to be small compared to the plate and far removed from the plate boundaries. Okay, so these boundaries are far from the hole. You see the geometrical parameter of our elliptical hole A and C. Um, the nominal stress is calculated based on the applied force and the total area. Okay, so sigma nominal here is P divided by A. Okay, so this is a very classical torsion stress, and sigma nominal is P divided by A. KT, geometrical stress concentration factor, is 1 plus 2 multiplied by A divided by C. Okay, so it's beyond the scope of this course to explain how this KT is developed. Okay, is developed analytically based on some theories, but we see that KT only depends on geometrical factors A and C. So this hole creates some stress concentration. This is an abrupt change in cross-sectional area, and now we have our stress concentration factor. A is the half width of the ellipse and C is the half height. Clearly, as the height of the ellipse hole approaches zero, so C approaches zero, creating a sharp edge, so it goes to the shape of a crack, and the stress concentration goes to infinity. So once basically this C becomes smaller, this elliptical hole becomes very similar to I could say a crack with the sharp edges, and the stress concentration will increase and the stress basically goes to infinity. When the hole is a circle, A is equal to C and KT will be equal to 3. Figure also shows a plot of KT as a function of C divided by A, the reciprocal of the ratio in above equation. The function is asymptotic to KT equal to 1 at large values of C divided by A. So here you see that C divided by A goes to infinity, KV will be equal to 1. So we could say that if C also goes to infinity, okay, so C becomes larger and larger, then this hole or the crack won't be opened by the forces. Or we could say the crack will be closed by the forces, and this shape here at the middle won't have any effect on a stress concentration, and Kt will be equal to 1. But if C goes to 0, then the crack could be opened by the forces, and at the tip of the crack we'll have a stress concentration, and the basically stress could go to infinity. So here we have a static force, and we managed to find a geometrical stress concentration 5. Complicated geometry is often necessary for the proper function of machine parts. For example, a crankshaft must have a particular contours for its purpose. The designer is always faced with the problem of stress concentration at sections having abrupt changes of shape. The best that can be done is to minimize their effects. So we need to basically minimize the effect of a stress concentration. A study of the stress concentration curves for various geometries in Appendix C will show that in general, the sharper the corner and the larger in magnitude the change in contour, the worse will be the stress concentration. Okay, so refer to the Appendix C for different shapes and find out how we could calculate geometrical stress concentration, and see that with the sharp corners and edges, the stress concentration will be higher. Okay, so we need to avoid stress concentration by any way, and methods to avoid that are as follow. We should, or we could avoid abrupt and or large magnitude changes in cross section if possible, or avoid sharp corners completely and provide the largest possible transition radius between surfaces of different contours. So here we have a couple of examples. You could see how we could avoid the stress concentration. You see that the stress, it's somehow like a fluid flu. So this is basically a flow of fluid or water or a stress, and you see that when we avoid these abrupt changes like here or sharp changes, the stress will be reduced. So this one here we have very sharp and abrupt change. This one we use this radius for the uh, radius. So you see that now we have more smooth stress flow and stress concentration reduce. This one also is another method to reduce with groove. Here we have a groove, and you see that we have a smoother now stress flow and stress concentration reduce. So this one is shaft, and this one is a bearing that sits on the shaft. We need a step to have a place to accommodate the bearing on the shaft, but you see that we could have a different type of mounting, and these different type of mounting will end up with a different type or level of stress concentration. Here they are using washer, okay, and they have this smooth fillet here that also reduces stress concentration. Here we have keys and keyways. These are basically a method of mounting gears on shafts, and you see that we could have a different type of keyways, and one of them, for example, is a woodruff, and the woodruff, you see that the abrupt change or the uh, gradient of the change is much less than the normal square keys. Okay, so um, we will discuss this one or these methods when it comes to the mechanical elements like bearings and gears, and we'll discuss how we could mount and install these different mechanical elements on shafts, and how we could avoid also stress concentration in some of the methods. Here we have one example that has some or could potentially have some level of stress concentration. We have a bracket as before, but we could see that here in the cantilever beam, we have this fillet, and this fillet could cause potentially some stress concentration, and we need to take this one into account. The cantilever bar in figure is made from a ductile material, so this is very important, and is statically loaded with Fy equal to 150 pound force. Okay, so here we have Fy, and Fx and Fz both are zero. What I could recommend you to solve the same problem once the Fx and Fz's have some values. Okay, so it could make the problem more complicated. So you could do it for practice. Analyze the stress situation in the small diameter at the shoulder at A by obtaining the following information. So here we have a shoulder, and this is a point A. Here in this example, we have a hint that where is the critical cross section. Yes, so they are helping us by pointing to the point A and say, look, the point A most likely is the critical cross section. But in reality, it's up to us to find the critical cross section. So it should be either the base cross section here, so it could be either point O, or could be a point A because of a stress concentration or because of the reduced diameter at this cross section. So in reality, we need to check both of these cross section and see either O or A has the maximum stress, and do the calculation for both of them. A, determine the precise location of the critical stress element at the cross section at A. Okay, so again, we know already that this is a critical cross section, and here not because of specifically stress concentration, because the load is static and the material is ductile. So geometrical stress concentration KT will be equal to 1. So we could say that there is no any stress concentration, but the issue is that we have a radius diameter at this point, and the radius diameter will cause a maximum or higher stress at the point A because of a lower moment of inertia I. Sketch the critical stress element and determine magnitudes and directions of all stresses acting on it. And for the critical stress element, determine the principal stress and the maximum shear stress. You have all the geometrical parameters and the values on the figure. All the diameters, you could see the diameter here is bigger than this section. And we also have the fillet radius in case is needed. Okay, so we need to find first shear force bending moment and the torsion torque. It's very similar to previous examples. Here we have the numbers. Double check how these or where these numbers coming from. Okay, For example, why we have 11 here, not 9 or 2 or any other numbers, yes. And I and J are calculated based on the diameter here at this cross section, yes. So we said that although notches or fillets in ductile material doesn't create specifically a stress concentration, but we need to take into account the radius, diameter, or cross section that they cause. Okay, so here the D is equal to 1 inch, not 1.5 inch. Okay, so we are uh, basically putting our calculation based on the diameter on this section. Okay. Okay, so at the point A, we have this stress element. It's our task to find the sigma x and tau xz. The sigma x is kt multiplied by sigma nominal, and sigma nominal is mc divided by I. Kt is equal to 1 because we have a ductile material. In case, for example, we have a brittle material, you have to calculate Kt based on the radius of the fillet, and the appendix of the book we have specifically the same beam with the fillet, so we could use this diameter here or bigger diameter or smaller diameter and the fillet radius to calculate Kt. But for the ductile material, which is the case in this example, Kt will be equal to 1 because the load also is static. We have mc and I, and we could calculate sigma x. Tau xz is tr divided by j. Again, kts is also equal to 1. Otherwise, we need to take that into account and calculate kts. So we could now calculate the tau xz. So as you could see on the stress element, we have sigma x and tau xz. You could use a Mohr circle to find tau max, sigma 1, and sigma 3. But here, instead of using Mohr circle, I'm using formulas. These formulas, again, could be also calculated based on Mohr circle. So I recommend you to use a Mohr circle also and check the results by the numbers you have on the slides. Okay, so this was the example for stress concentration. The load could be dynamic or the material could be brittle, and then we have to calculate Kt. Now we move on to another topic, axial compression columns. The outline of this section is as follows. We'll talk about the concept of buckling, slenderness ratio, short-long columns, Euler column formula, end conditions, buckling tests, and intermediate columns. A column may fail by buckling rather than compression. Buckling occurs suddenly and without warning, even in ductile materials, and as such is one of the more dangerous modes of failure. A short column will fail in compression, and its compressive stress can be calculated by above formulas or the formulas that we already presented and discussed. An intermediate or a long column will fail by buckling when the applied load exceeds some critical value. The compressive stress can be well below the material's yield strength at the time of buckling. So why buckling is important to us? Because all the topics we covered so far is based on stress and and calculating principal stresses. And as we will discuss later in a failure theory, we will use those principal stresses to compare uh, or find the effective uh, effective yield strength. So we will calculate the effective stress and we'll compare it with the yield strength and see if the material will fail. But in the buckling, the failure is not because of stress at all. And we'll discuss this phenomena. And the buckling is very dangerous phenomena because it develops and happens very quick. So we must avoid that in columns. So here we have columns. See that the difference between columns and beams. Beams usually carry transverse load, but the columns carries compressive loads. In columns, we have some geometrical definitions like a slenderness ratio. The factor that determines if a column is short or long is its slenderness ratio SR. SR is L, or the length divided by K. So where L is the length of the column and K is its radius of gyration. Radius of gyration is defined as K is equal to a square root of I divided by A, where I is the smallest area moment of inertia of the column's cross section about any neutral axis, and A is its area at the same cross section. So I is moment of inertia and A is area of the cross section and L is the length. So we could calculate a slenderness ratio. So you could see if we plot the free body diagram of half section of the column, we'll have force P or compressive force P and the bending moment M at the middle. A short column is defined as one whose slenderness ratio is less than about 10. The material's yield strength in compression is then used as the limiting factor to compare to the stress calculating in above equation. Okay, so for short column, buckling would be hard, and the definition is that if the slenderness ratio is less than 10, we have a short column. And we need to calculate the stress, compressive stress, and compare it with the yield strength of the material. A long column requires the calculation of its critical load, which we will discuss in coming slides. Figure on previous slide shows a slender column with rounded ends acted upon by compressive forces at either end, which are coaxial and initially act through the area centroid of the column. The column is shown slightly defected in the negative y direction, which shifts its area centroid out of collinearly with the applied forces of or at its end. So here you see that it's already deflected. The column is deflected. This is a long column and a slender column, okay? This shift of the area centroid creates a moment arm. This is a moment arm here for the force to act about and puts the member in bending. as well as in compression. So we have both compression and bending. The bending moment tends to increase the lateral deflection. So deflection will increase, which then also increase the lateral deflection, which then also increase the moment arm. Okay, so now we have a positive feedback. And that positive feedback will cause that the sudden buckling. Once a critical value of load PCR is exceeded, the positive feedback of this mechanism causes a sudden catastrophic buckling, and there is no visible warning before failure. So if P increases, and then suddenly reaches to the PCR, then very quick, the column will collapse. Okay, now let's do some calculation to have a better understanding of buckling. We need to calculate first bending moment M. So assumes that we have a small deflection Y. Okay, so this is a Y here, the small deflection. The arm, this is the arm of the force P. Now the moment is equal to P multiplied by Y. We had already this equation that M divided by EI is equal to the second derivative of Y. Okay, now we need to substitute M in this equation, and we'll have this second order differential equation, where here P is P, E, and I, all of them are constant, so Y will be dependent variable, X is independent variable, and P over EI is constant. What is X? X is the distance from coordinate system to any point across the column. Okay, so based on differential equation, we could find the general solution for Y, which is C1 sine of square root of PIX plus C2 cosine of square root of P divided by EIX. C1 and C2 both are constants here, where C1 and C2 are constants of integration that depend on the boundary conditions defined for the column of figure as Y equal to 0 at x0. So at this uh, at, uh, at this support here we have our first boundary condition. So Y or deflection at the support will be 0 at the x0, and the deflection at XL or second support also will be 0. So if we use these boundary conditions, we should be able to find C1 and C2. Substitution of these conditions shows that C2 is equal to 0. So you could simply test that, put here X as 0 and C and Y as 0 and see what are values of C1 and C2. You will have two equations that you could find C1 and C2. So you will see that C2 is 0 and C1 sine of square root of P divided by EIL is equal to 0. So C1 should be a non-zero constant, because then we will have a trivial solution, and Y always will be 0, which is not true. Okay, so we know that C1 is not 0, and then we could move on and find P. So now we have this equation. This equation will hold if C1 is equal to 0, but this is a null solution or trivial solution, so C1 must be non-zero, and sine of square root of P divided by EIL is equal to 0, which will be true for a square root of P divided by EIL is equal to n pi, and n could be any integers from 1 to infinity, okay? The first critical load will occur for n equal to 1, okay? So this is basically the lowest critical point, and we are interested in the lowest one. So P critical then will be equal to pi 2 EI divided by L square, okay? So now we have our equation to calculate a critical force. Okay, so we calculated critical force, plus we had some definition of slenderness ratio, SR. If we combine these equations together, we will have Euler-Coulomb formula. So this formula is known as Euler-Coulomb formula for rounded end or pinned end columns. So remember that this formula is calculated based on these specific boundary conditions. Note that the critical load is a function only of the column's cross-sectional geometry I, its length L, and the material's modulus of elasticity E. The strength of the material is not a factor. So that's why buckling is important to us, because um, this is a different type of failure. Okay, it's not based on the strength of the material, it's not based on the stress. It happens because of another phenomena that now you should know better, because of the feedback loop that happens, and that feedback loop will suddenly cause buckling. Okay, so here we have Euler-Coulomb formula. We could have different other end conditions. We discussed rounded end conditions or pinned, and we developed that formula based on these two boundary conditions. But we could also have fixed free, so one end is fixed, the other end is free, or we could have fixed pinned or fixed. So these are also different types of end conditions. To take into account these type of end conditions, we could have another definition for a slenderness ratio, which is equal to L effective divided by K, and we'll have a table to find L effective for different end conditions. Here we have a table that shows L effective for different end conditions. We could use the same Euler formula which we developed for the round or pin end conditions, but instead of using SR, we'll use this formula for the SR, which takes into account the L effective. For example, for fixed free, for theoretical value, we instead of basically L, we'll use 2L, so L effective will be equal to 2L, or for fixed, the L effective will be half of L, and then we'll use the same Euler formula to find P critical. Okay, so here also in this picture you see how they are testing columns. with different end conditions. For example, we have pinned or fix or pinned fix and free fix, and they apply load and see if the load reaches to the critical value before failure. Intermediate columns and Johnson formula. This figure shows um, basically how both compressive stress and the buckling could cause failure and safe region. Y-axis is P divided by A, and the x-axis is a slenderness ratio, SR. Here we have compressive yield strength or SYC, okay? So don't mix SYC with SR, okay? So these are two different basically animals. These are two different stuff, so don't mix them up. So SYC is compressive yield strength, the SR is slenderness ratio. So at SYC or compressive yield strength, the material will yield or will fail. Okay, so so it doesn't matter how much is SR at this point. For sure, the column will fail. So that's why we have this horizontal line, and is mostly used for short column. Why? Because we said that short columns have slenderness ratio less than 10, and you see that from 0 to 10, this line will be the limiting factor for safety and failure. Okay, so below that we are safe. Above that, the column will fail. This line is basically Euler line, is based on the Euler formula we developed. Okay, so P divided by A is pi square E divided by R square, and SR is the dependent variable here. So if we plot it, we will have this curve. So based on this formula, below that we are safe. Okay, so this is an Euler region, and above that the buckling of the column should happen. And this part is for long columns. The issue is that these are a theoretical formula. Like this Euler formula is a theoretical formula, but in reality, in empirical experiments, they've seen that columns could could fail or buckle even in this safe region of ABC. So then Johnson tried to define a new safe region, which is combination of both compressive yield strength and Euler formula. So what he did, he fitted a parabolic curve to connect the A to D point. Okay, and what is D? D or the Y value of the D is half of SYC or compressive yield strength. So to find the Johnson formula, we need to first find point D location, or we need to find SRD value. So SYC divided by 2 is equal to P critical divided by A, which is equal to pi square E divided by SR2, so we could find SR at the point D. So this is SR at the point D. If we use these basically 3 points A, D, and C, then we could calculate the Johnson formula. This is a Johnson formula that shows the safe region even for the experimental columns. Okay, so if we follow the Johnson formula and calculate P critical, then not only in the theoretical but also in practical, the column will be safe. For other type of columns, I mean with the different end conditions, what we need to do, we need to find the L effective and use the L effective in Johnson formula.